Welcome back. It looks like this is the second last page of thermo practice, so of course they're going to throw some final boss questions at us. Let's see what they have. So, the formation of potassium chlorate. This is potassium chlorate, KClO3, and if we're forming it, it comes from its elements, which will be potassium, chlorine, and oxygen. Potassium is a metal, chlorine's a diatomic gas, oxygen's a diatomic gas. If we're balancing this, 2 and 3 on the oxygens makes me want to go to 6, my common multiple, and now I need 2 potassium there, and I need 2 chlorine, which I already have. So there's a balanced chemical reaction, and if we want to make it thermochemical, we need to do a delta H calculation. Our enthalpy of reaction is going to be the products, 2 times KClO3, which is potassium chlorate, which is minus 397.7, minus, can we agree these are all going to be zeros because they're all pure elements? That would save us a bunch of time. And 2 times minus 397.7 is minus 795.4 kilojoules. So that is our enthalpy of reaction, energy of reaction, reaction and energy, words to that effect. Okay, now that we have that, that is our thermochemical equation. Let's see what they want us to do with it. Rats. I wanted to drag that down. I guess I'll just have to take it with me. Find the amount of heat transferred when 1 gram of potassium chlorate is produced. So, in this reaction, if we're making 1 gram of KClO3, our molar mass would be 39.10 from the potassium, 35.45 from the chlorine. Oxygens are 16 each, but we have 3 of them. That's 48. I get 122.55 grams per mole for our molar mass, and that means our number of moles is 1 divided by that number I just said. Where's my reciprocal key? New calculator, can't find the reciprocal key. I have to do it the hard way. 1 divided by 122.55, 0.0081599 moles of potassium chlorate. Okay, so our enthalpy change is going to be N delta H. It's our number of moles, which we just found. 81599 moles KClO3 times, and our delta H will be 795.4, but that's not all. What am I going to say after that? 795.4 kilojoules for every 2 moles KClO3. Moles cancel, and we get 795.4 divided by 2, 3.25 if we go to 3 sig digs kilojoules. This reaction is exothermic, so it releases heat. You could either put a minus on here, or because they asked in English, is the heat released or absorbed, I would be inclined to answer in English and say energy is released. Hope that seems fair. Okay, now there's a part C here. Excuse me while I move some stuff around. I just want to take this thermochemical equation and move it down so I can use it some more. Rats. Okay, I'm going to have to erase some of that green stuff. Sorry. Okay, I can live with that. You saw that was 3.25 for the B. Answer B. We'll be okay for now. Okay, so new thing. They tell us we start with 10 grams. My alignment's out of whack. I apologize. There we go. Okay, they say we start with 10 grams of potassium. So here we have a mass of 10 grams. And this reaction is going to happen and it's going to produce some heat. And then they say, how much water could we heat up using that heat if it absorbed what comes out of the reaction? So you remember doing these at the very beginning of the thermo section. We had a formula that says energy equals mc delta T. They're telling us the delta T effectively. They give us the original and final temperatures. We know the specific heat for water. We're supposed to find the mass of water, and this energy is going to be whatever comes out of our potassium reaction. So we have to get this part done first. We have to do energy equals N delta H. This will tell us how much energy the reaction makes, and then we'll take that energy over to here and calculate a mass with it. Our mass is 10 grams. The molar mass for potassium metal is 39.10 grams per mole. And so our number of moles is 10 divided by 39.10. Zero 0.255575 moles. Energy equals N delta H equals that number I just said, 0.25575 moles of K times, our reaction says we get 795.4 kilojoules for every 2 moles of K. 2 moles of potassium. Multiply that together, 795.4 divided by 2, and we get the energy released is 101.71 kilojoules. Okay, so now the question is, if you have 101.71 kilojoules, how much water can you heat up, as described there? Our heating up material formula is energy equals mc delta T. The energy going in is 101.71 kilojoules equals a mass I don't know times 4.19 kilojoules per kilogram degrees Celsius, because we're talking about water, and the delta T is 25.9 degrees Celsius. Note, because this energy was in kilojoules, I had to give my specific heat in kilojoules per kilogram degree Celsius. I'm normally a joules per gram degree Celsius guy, but because of these units, I was kind of stuck doing this. Not so bad, but make sure that those units match or bad things will happen. Another note, I've run this calculation once already, and I'm not getting 916 grams, so I think this is an older version of the workbook where the key was a little out of whack. You're about to see a number come out that does not match this, and I have been over these calculations, and I think I'm doing everything right here. So I think you can trust this video, and I'm going to follow up after this and make sure that the workbook's updated. So try not to let that bother you. If it does, check with your instructor, and they can confirm that you're trusting the right stuff. So to solve this, 101.71, we're going to divide by 4.19. We're also going to divide by 25.9. And I get that thing out of there, a mass of 0.9372 kilograms. We're restricted to 3 sig digs, so that's going to become 0.937. You could either say 0.937 kilograms, or if you take kilograms and multiply by 1,000, you get 937 grams, which is also fine for 3 sig digs. So I'm going to say, pretty sure there's a mistake in that number, and 937 should be good here.